Welcome back to part 2 of the lecture 10, OpenFoam software and CFD application from the High Performance Computing Advanced Scientific Computing course. In the part 1, we looked at the environment of the OpenFoam and the setup that is required to be done on the decompose pardict directory. And we talked about the available method for the decomposition. Also, we had a short review on the MPI approach and how we can split the domain of the problem of the CFD to a subdomain and assign each subdomain to the processor. In this part of the lecture, we will continue about the OpenMPI and the boundary condition which is necessary for the MPI domain. And then in the last part of this lecture, we will have practical example of the OpenFlow for parallel decomposition and running the simulation. So this is second part. And firstly, let's look on the domain boundary. What is the domain boundary for the MPI? Indeed, in addition to knowing who is the neighbors for each processor, who is the neighbor for each subdomain, each processor needs to know whether any of its boundary is a fact of a physical boundary or not. Since in the CFD we are dealing with physical boundary, it is required to specify the boundary condition for the subdomain. If you remember in one example, we divided a 2D domain to 4 or 6 subdomains, and there was some overlap between these subdomains. It's very important to swap the data and the information between them, which is something related to boundary condition. Why we need the boundary condition to be specified? Indeed, to avoid the programming error and to apply the boundary condition correctly. Because when we have the incorrect information about the boundary condition, of course, we don't get the right solution. Regarding the boundary condition, there are two cases, the periodic boundary condition and non-periodic boundary condition. We will have short presentation about these two cases, and we will see how we can use them in the CFD public computing, especially for the OpenFoam, and you will see it practically. Let's first start with the periodic boundary condition. In the periodic boundary condition, the map of the neighbors should reflect the periodic boundary condition. What is mean? It's mean in the periodic boundary condition, the blocks at the end are treated as any other internal block by just defining the correct map of their neighbors. For example, here we can see example of the subdomain from domain of the problem. We have the processor number 0, 4, 8, and 12. And here, since the boundary condition next to 12 and next to 0, we are specifying the neighbor for 12 is the processor 0. To do that, here you can see a simple command which for processor 12, the neighbor is the right one, which is equal to 0. And for the process 0, the neighbor is the left side, which is 12. With this setup, we are using the periodic boundary condition. And in this regard, it's helping to keep the physical boundary of the domain and get the right solution for the problem. Also, sometimes the geometry also important is depend on the geometry of the problem, which how we can specify the periodic condition, boundary condition. But in this example, simply you can see for this kind of the subdomain, the setup in this way. The another case is non-periodic boundary, which in this approach we should avoid or sending or receiving data from a non-existent block and apply the boundary condition. A simple way to make this task using the MPI content handle, which is MPI person null. To do that, also we look at this example with processor 0, 4, 8, and 12. The processor 12, which is located in the boundary, we can say the right neighbor for the 12 is MPI post null. So this making its non-periodic boundary condition setup. In this blue block here, you can see the how we specified these non-periodic boundary conditions for this kind of a problem. Indeed, we need to cover two features: avoid sending or receiving data from a boundary with this setup, and also making the boundary condition based on the MPI post node. So this is the example from two cases of the boundary condition, periodic and non-periodic. Since in the CFD problem, we are dealing with boundary condition, and one of the important part of the required information with the CFD problem is the boundary condition. We need to choose the correct way in the MPI setup to explain and define the boundary information for the domain and the subdomain to get the correct solution. In this lecture, we started with the environment of OpenFoam, and we had position from the OpenFoam and how we can do the setup. And then we looked on the example of the batch, which made for the alias system, and we will see it practically. We saw how when we split the domain of the CFD problem to subdomain, depend of the geometry of the problem, we can have a different subdomain in the shape and the geometry. However, the important thing in the MPI to assign each of these subdomain to one processor. Also, we talked about this boundary condition to make the problem match the boundary. And there are two approaches, the periodic one and non-periodic boundary condition. And we had these examples from them. Now, let's have the practical example of this application. When we go to alias system and we open the batch file that we have, this is the batch file set up for this application. I will share this batch file with you, and you can use it. So as you can see here, we need to specify our email or user and the partition, number of the node. Of course, we can increase the number of the node, and also task per node depend of the task per node. It's very important to be equal to the number of the subdomain of the problem, the memory per CPU, and the maximum time of the running. And also we have output of the report of the job, and also if there is an error. Here we're making the directory and loading the required module for the OpenFoam. Indeed, for OpenFoam, we need case of the OpenFoam CFD to run it on this simulation. We made it simple here to since there are some students, they are not in the field of the fluid dynamic. Maybe it's so difficult to prepare the case from the OpenFoam. So we made it simple here. We can copy a case from the foam tutorial, which is available online. And also, because OpenFoam installed on the cluster, it will take copy from the tutorial here, and we don't making any change to the original one, only there is a copy, and then we can run the simulation. One thing is important here about the decompose pardict directory. Here we need to specify the number of the subdomain and also the method we are using for the decomposition. As we said, it's one of the important part here. Also, we made it simple. We created one as a setup, and always you can do the setup there. Then the copy, it will be copied from this main file to the new case when you bring it to your directory. Then generating the meshing and making the composition and running the simulation with its solver. Of course, each case of the OpenFOAM has a solver, and you need to run in parallel with its solver. And in the end, we can make the reconstruct part and gather all the solution to visualize it. Regarding the visualization also, we have the Power View. The Power View is installed on the Elia system, and when you write the command of the Power View, you can see the visualization. So this is the to run the simulation. Let's look at the. Let's go back to the case here. As we said, here we are using the Pitts Daily case, and how you can bring these cases. You can go to the GitHub for the tutorials of the OpenFOAM. You can search it and you can find it. As you can see here, all the cases are available. This is helping you to find the tutorial directory, because you need to write the directory here on the copy section to copy. To make that, there are two options. If you have OpenFOAM in your system, it has a tutorial and you can find the directory for the case. And if not, you can Google the GitHub and you find this repository for the OpenFOAM. As you can see, the name of each directory is based off its categorized case. For example, when we look at the incompressible one, we can see the simple form. This is name of the solver. This is the thing that you need to write it here when you run the solution. For example, if we use this example here is from the Pitts Daily, when we are going to simple form, we can see the Pitts Daily example here. And when we are going on it, here you can see this directory. Same as it's written here in these directory address, incompressible, simple form, and Pitts. Here also it's same. So this is the same also in your OpenFOAM. It's in your system, and also same on the OpenFOAM on the Elia system. For example, we can have a look at the again these simple form, and you can see this example from motorbike when it was run on the real scale cloud computing. If you are interested, you can set up your address on this one and run this simulation. Now let's see the simulation. For example, do one of these example. practically, firstly, I need to go to this directory because I set up, always pay attention to your directory when you want to submit a batch. PC course. And here we have the OpenFoam. Here we have the batch file. The batch here, it's this one, the number one. And we saw its setup. We are using the pits daily. And here the setup, we will run this one. And also we can try with another one. Uh, so here I can just run a batch. Just I need to check something else also. Because here we made this directory and the copy file will go to the run. Since I made this run before, let's look if this file is available. I need to remove it. As you can see, the pits daily and depth chart 3, maybe we'll make it the next one. Let's delete these two. So we don't have them anymore here, because when there's a copy from them, because the decomposition is done, you will get error. The copy it's fine, but when the decomposition it's running, because it will see the decomposition as the subdomain are available, it will get error and stop the simulation as running. Now let's submit the job. You can see its ID here, so let's see it's running. Yes, it's running now. Of course, we expect to get email also when we're running the problem on it. It's ended here, and you can see the number of this case is 698. We expect to see the report here. As you can see, the error here, what is it? So this is the sum about the node, which is specified here, but it doesn't impact the running. We are not sure about the node, this Uton node here, the setup we are using. We need to check how many processors are available. Maybe this because of this problem. How the running it's done, and here we can see the report. This is the one of the important thing on the OpenFoam. When we look on this file, we can see in the sequence what's happening. First one is the black mesh, is generating the meshes. And then here we have the compose part. Regarding the meshes, we can see how many meshes are available here, as you can see. And the faces they are available, how many cell, how many point, all of them, you can read them here. When we look on the decompose bar, we can see how many processors created. We did the setup on 4, so we expect to have 4 processor 0, 1, 2, 3, there are 4. You see how many cells are available, how many shared faces. With processor 1, with processor 2, this is the overlap that we were talking about it. and again, number of the processor of the boundary faces, how many they are. This is the between each mesh or each node of the element of the subdomain. And here again, you can see this information. In some type, there is a QL number and somehow no. For example, when we have the processor 0, overlap with number 2, and here 0 overlap with 2, as you can see, they are 118, here also 118. And also this is about the 30 and 30, and you can figure out how they are connected. Then after that, the simulation for the parallel computing is done here. Of course, you can see the information here, what setup on this is something related to the setup of this problem. We are not going to talking too much about it. There are some setup on the directory of the problem it's required to be done, and this is the solution. And you can see the time of this solution, and when it's ended, here you can see the fundraising parallel one, and how many iterations happening, and how long time it's taken to run this simulation. Indeed, as you can see, the setup was simple and convert to with 229 iteration. And here the reconstruct part also gather the information and create the result for this simulation. Let's have a look on the decomposed path file also. We said on the batch file here, we are doing the setup before the running. If we look on this setup here, for example, we specify number of the domain 4, and the method it's selected here. The method it's simple. We have these different methods we can choose, but front of the method we write simple, so we choose this one. And regarding the number of we need to specify the coefficient here, as we said in the X and Y direction. Here is specified 2 and 2. So in this kind, we're making the decomposition with the OpenFoam. We can run the Power View to watch the result also. If we need to load this module on the main environment of the area, and then we can write a Power View. So we can have the Power View, and we can look on the result of this solution. And go to the run. This is the pleats, and here there are the results. For example, when we apply the form file, we can see these result of this simulation. This is for the pressure, for example. We can have the velocity, for example, and we can run it, and we can see how it's going. It's a for short time, very short period of the time, only 3 time steps, and we can see the result. For the P also, we can try to look what's happening. So this is a simulation when we are running in parallel, and you can see. Of course, if you are interested, you will be able to run any case of the OpenFOAM as I showed you here. You can go to the tutorial and choose your model. I suggest you, if you are interested for the assignment or final project, you can take the model from the 3D when you go to incompressible flow. And simple form, here you can see the motorbike, and you can run this simulation also. The another example I can suggest you, it's from the maybe the compressible flow. If it's from the multi-phase. From the multi-phase, when we go, we can see the compressible interform from the laminar. If you remember from the previous lecture on the introduction to OpenFoam, we run this model, so you can use this address and run this one, the directory, and you can run the 3D also. To run the 3D, you only need to take this address and add it to the batch file here to make a copy from it. So it's multi-phase. And you can make this setup here. And just replace it with this one. Then you will have this running example. Here you need to change something also to match with it. Here you need to change this to run the simulation. This one and this one. This one will replace. Of course, I suggest you because it's 3D simulation, so it's good to change the number of the subdomain. You can keep it on the simple when you are going here and open these setup for the decomposition. You can, for example, make this 8 or 16. If it's 8 and you keep it on the simple, the coefficient for simple, for example, it could be 2, 4, and then it will be 8. 2 times 4, it will be 8. So it will work for it. Then you don't need to do anything else about it. You will run it and you will get the simulation. However, because it's 3D, the running will take longer time. And again, you need to submit a batch. We need to close the power view. Then we're going back to our directory. Here, if we run the S batch again, the next work will be started to running. If we don't have here the 3D one, we can submit the S batch. And form one, and you can see the number of the job here. It seems is running here. It stopped, so it seems maybe there is some error. Let's look if there is an error here. The error here is number 3. Okay, let's look as is expected. We made them 8 there, so here they should be 8 also. Of course, we can look at the error to see what was the problem. Yes, of course, it's about number of the domain, so we correct it now. We expect to write again. Just let's look if it's available. If anything copied from it, let's delete it. No, nothing here. So let's submit the job again. And see it's running. Yes, it's running. And however, because it's 3D, we expect to have longer period. We can see the output of this one. If we refresh the page, we should see the report of the 700, which is here, the output. Okay, it stopped again. Let's look what there is an error still here. Here, some error above the computing node. Okay, something we forget to change it. As I told you, we forget to change the solver. The solver here for this model, as we said, the solver is compressible interform. So we need to write it here and replace it for every type of the problem. We have different solver, and it's important to change it. Compressible interform. This the solver for this type of the problem. So this is the directory, this is the command, and this is the decompose predict, and this is the compressible interform. So this is the setup which was required to do it here. Now we can submit the batch. So this is 7.1. If we refresh this page, we should see the output. As you can see, only one error here, which I think regarding the computing node. Okay, it's just replaced some. Okay, so the again, because the previously it's created on the directory, we need to stop it and remove the previous one, then run it again. How it's continue here? Always when we run it again, we need to remove the previous one, because this one was here. There are some error, which is mean the subdomain is created before. However, now you know how you can run it, and you know the game to run this kind of simulation and see it's running. For the report of the simulation, when you open this file, you can see the simulation and the running of these parallel solution of these problems. Now it's in the part of the solver. It didn't create the decompose part, as you can see here. It doesn't show the processor because they are created on the previous run. We forget to delete them, so it's continued on that part. And the error it's mentioned here because of this availability of the previous run. So this is the approach that you can need to. You can run the parallel solution for the OpenFoam. There are some setup on the batch file specifying the case that you need it. Pay attention to this solver, which is relevant to the case you are using. And also the decompose predict file. You need always make the setup on the number of the domain and the method you need to run. And this is everything. So you will be able to run your simulation. So here our part 2 of the lecture 10, it's finished, and you know much more about the OpenFoam software and parallel application for the CFD. In the end of the lecture, there is a video. I suggest you to watch it. It's from the Alter CFD, which show how the CFD simulation helping to see many feature of the flow around the object and the machinist. And you will have the link of this video in the reference of the this slide. We will continue in next lecture about the CFD and more application from the HPC in this area. Thank you.